Hello guys, warm welcome to today's session. We are looking at problem number 2, which is still under application of differential equations, and this is a population problem. So this is the question: suppose the population of mosquitoes in foothold increases at a rate proportional to the current population, and in the absence of other factors the population doubles each week. There are 200,000 mosquitoes in the area initially, and predators, birds, etc. they eat 20,000 mosquitoes per day. Determine population of mosquitoes in the area at any time. Okay, this problem is actually one of a kind, and over the years there are a lot of speculations about the way this problem should be solved. So I'm just going to show you a version of how to tackle this particular problem. Okay, so let's dive into the solutions right away. So solution to this particular problem. So first off, we are going to examine the lines of the question or the word problem carefully. But before we do that, I want you to know that for population problems, the rate of change of population is actually governed by this particular equation. That's the P dt is actually governed by increase rates minus decrease rates. Okay, so this is the first thing that you assume okay, for population problems, where P itself represents the amount of mosquitoes present at any time. So P of T is the amount of mosquitoes present at any given time T, for instance. Okay, so let's move further with this. Now we are going to obtain our increase rates and our decrease rates respectively. Let's start with our increase rates. So to get our increase rates, we are given in the body of the question that suppose the population increases at a rate proportional to the what? Current population. So the rate of increase is actually proportional to the current population. So in the increase rate, it will also take this form, that the P dt for the increase rate scenario is proportional to the current population, which in this case is P. So introducing your constant of proportionality, the P dt becomes Kp. Is that okay? Kp. Then how do we get our decrease rates? How do we get our decrease rates? So let me just use this one as equation 2, for instance. I'll get back to the increase rates. Then for equation 2, for decrease rates sorry about that. The decrease rates, they said that there are 200,000 mosquitoes in the area initially, and predators, we have birds, etc. they eat 20,000 mosquitoes per day. Is that okay? So there is a decreased rate per day, and that is actually 20,000. Now take note, decrease rate is mosquito per unit time. Is that okay? The rate of change in mosquito, or the rate of reduction in mosquito per unit time, and it's already given to us as a constant factor that every day 20,000 mosquitoes goes away. So the decrease rate now is just equivalent to 20,000 mosquitoes per day. Okay, this is equation 3. So the central equation now, equation 1, now transforms to this form, that dp dt is equal to Kp for my increase rate according to what we have here, then minus the decrease rate, which is 20,000. So this equation 4 is the model that we want to use to solve this particular problem. Now, solving this particular problem, we are going to work with some other assumptions based on what we have derived from the word problem. Now, before we solve this problem, first things first, let's determine K. So let's determine K. So how do we determine K for this particular problem? Now go back to the question. Now they said that, right, suppose the population increases at a rate proportional to the current population, and in the absence of other factors, the population doubles each week. So in the absence of other factors, the population doubles each week. Okay, so look at the original equation, or look at the central equation or our central model. Okay, this central model captures both the increase rates and the decrease rates, and the decrease rate is as a result of contribution from other factors. Now look at the equation for our increase rates. Our increase rates and our entire model is just almost the same with each other. The only difference is that we have in the equation that takes care of other factors, we have a minus 2000, but in the ideal case we just have that dp/dt is equal to what? Kp. So we are going to use this ideal case, okay, according to what the question tells us here, that in the absence of other factors, the population doubles each week. So we are going to use this simple statement coupled with equation 2 to determine the value of K like this. So from equation 2 we have that dp/dt is actually Kp. Okay, so if you separate the variables, you have 1 over p dp is equal to k dt. Now when you take the antiderivative of both sides, antiderivative simply means the integral of both sides. So when we take the antiderivative, what are we going to get? That's right, so on the left hand side we're getting a natural logarithm of p, and on the right hand side we're getting a kt plus c. Is that okay? Now if you take the exponential of both sides, you're going to get exponential ln p is equal to exponential kt plus c. Now let it be known to you that this right hand side is still exponential kt dot exponential c. Remember, am plus n is actually am dot an. Okay, so that is why this side becomes like this from this side. Now if you call this exponential c another constant, you can call it p naught, okay, if you want. So that's what we're going to use. Let exponential c be p naught. So our exponential ln p becomes p naught exponential kt, and remember the identity, that's exponential ln f is equal to f. So exponential ln p is equal to p, so p is equal to p naught exponential kt. Okay, so this is the ideal case. Now this is from the ideal case whereby our population is, the rate of increase of our population is directly proportional to the current amount. Now we want to use this ideal case to find K, because they said that in the absence of any other thing, that the population doubles per week. Now take note that the unit of our time this time around is not the conventional seconds, but the unit of time is day. So time is measured in days. Okay, so anytime we say a week, we mean 7 days, and so on and so forth. Is that okay? So there is kind of like a periodic occurrence happening in terms of weeks. Okay, so we have days, then we have weeks. So every week corresponds to 7 days. Now going back to the question, after we've gotten this model over here, let me call it 5. we are going to use some of the initial conditions that we were given according to the ideal assumption. Now, the ideal assumption lets us to know that in the absence of other factors, the population should double each week. So if I use this ideal assumption, okay, if I use this ideal assumption, now anytime you see a number in front of an exponential, the coefficient in front of an exponential is always an initial value. It's always a start value. Is that okay? So they're trying to tell me now that in 7 days, okay, after every week, the population doubles. So this is my P of t. This is my P of t. P naught exponential kt. So if the start value, for instance, is P naught, that's if the initial value is P naught. So they're trying to tell me that after 7 days, I'm going to have 2 P naughts, and so on and so forth. So after maybe 14 days, I'm going to get something like 4 P naughts. This is the ideal case without taking note of other factors. So this is the ideal scenario without taking note of other factors. Is that okay? So we just want to use this ideal case to obtain the value of k. So they are giving to us that P of 7 should be 2 P naughts. Is that okay? So if you replace P of 7 equal to P naught, means that P is equal to 2 P naughts when T is equal to 7. Okay, when T is equal to 7. And this 7, the reason I'm using it is because they said after a week, or after each week, the population doubles from the initial version. That's in the ideal case. So if you solve this particular equation with these initial conditions, you get 2 P naughts is equal to P naughts exponential k multiplied by 7. Okay, so P naughts cancelling out P naughts, you have exponential k, or exponential 7k is equal to 2. Now when you take the natural logarithm of both sides, so take natural log of both sides. So taking the natural logarithm of both sides means ln exponential 7k is equal to ln 2, and there is an identity that ln exponential f is equal to f, just like we saw that exponential ln f is equal to f. So these are inversely related identities. So maybe in another video I'll explain to you why it's like this. So take note of these important identities. So if ln exponential 7k reduces to 7k, then we have 7k becomes ln 2, so that k under the ideal assumption is now going to be ln 2 divided by what? 7. Is that okay? So let's keep this as a particular expression. Now, having gotten the value of k from the ideal assumption, we are going to slot it back into our equation. What equation did we derive? Equation 4. Okay, so we are going to slot it into equation 4 so that we'll get the model that governs this particular growth system. Then we are now going to simplify to get the final expression for p at any instance of time. So let's slot it in. So according to the model, if you pause the video and check it again, you will discover that dp dt, therefore dp dt is equal to kp, which is ln 2 over 7, then p minus 20,000. Okay, so let's continue. Let me see, this is my equation 7. So I want to keep going. So I'm going to solve it now. Of course, you know it looks like a linear first order differential equation. So you have minus ln 2 over 7p is equal to negative 20,000. Now, if you restructure this particular differential equation, you will have minus ln 2 over 7 like this, then p is equal to negative 20,000. So this conforms to the general form something like dy dt plus p of t y is equal to q of t, for which our integration factor, our if or mu of t, is exponential integral of p dt, and our solution finally will be what? Y times integration factor will be equal to the integral or the antiderivative of q multiplied by the integration factor dt. Okay, just to refresh our memories on the linear system. So for this particular one, you already know that this value is your p. So this p and this p, they are totally different. Okay, so this p is actually the coefficient function, which in this case is actually constant, negative ln 2/7, and our q is actually negative 2 times 10 to the power 4, which is our negative 20,000. Then we have our integration factor, our if or our mu of t, to be exponential integral of p dt, and if you simplify this by taking out the constant first, negative ln 2/7 integral of dt, which gives me exponential negative ln 2/7 then t. Now you watch what I'm going to do to this particular case to simplify it. Our integration factor is actually exponential minus ln 2/7 t. Now if I play with my law of indices a little, I'm going to simplify the nature of expressing this particular integration factor. So let's go together. You can still express it like this, in this way. It's actually exponential minus t/7 ln 2. Are we together? Exponential minus t/7 ln 2, and in this case is actually equal to exponential minus, exponential ln 2 raised to the power of negative t/7. Okay, so you saw how I used the multiplication relationship between different terms to actually group 7 and t together by saying minus 7/t. Then I now used the law of logarithm, a log m is still log m raised to the power of a, and in this case a is acting as the whole of this guy over here. That is why we have it like this. So do you remember our axiom that exponential ln f is actually f? Very good. So if you remember that axiom, our integration factor can still be expressed from exponential ln 2 raised to the power of minus t/7 to 2 raised to the power of minus t/7. So our integration factor is now 2 raised to the power of negative t/7, 2 raised to the power of negative t/7. So having established our integration factor, we're now going to say p times integration factor 2 raised to the power of minus t/7 is equal to integral of q times integration factor, which is 2 raised to the power of minus t/7, dt. Okay, and this time around our q is actually minus 20,000, if you can see it over here. So we have p dot 2 raised to the power of minus t/7 is actually integral of minus 20,000, rather not 2,000, then 2 raised to the power of negative t/7 dt. So let's see how we are going to resolve this particular problem. So how do we resolve this? So p dot 2 to the minus t/7 is still the same thing as negative 20,000 integral of 2 raised to the power of minus t/7 dt. Okay, this is where you might think it's challenging, but if we can just remember some of our little laws of differentiation and integration, we'll be able to integrate this guy without much hassle. We just need to remember some few principles, okay, some few tips to help us to actually see how to integrate functions of this nature. First of all, let's go back to a differentiation of functions like this. Assuming I give you 2 raised to the power of 8t and I ask you to differentiate it, for instance, where a is an arbitrary constant, you discover that the answer you get, first of all, is a, bring a down, then after differentiating 8t you get, with respect to t, you get a, and you now write 2 raised to the power of 8t ln 2, okay, a then dot 2 raised to the power of 8t natural logarithm of 2. This is the differential of this kind of exponential functions. So invariably they are trying to tell me that if I rearrange it, 2 raised to the power of 8t, it will give me a 2 to the power of 8t then ln 2 dt. Now what are the constants here? What are the constants here? The constants are this and this guy over here. Are you with me? Flow with me. So if the constants are this and this guy, so you agree with me that you can actually factor them out. Is that okay? Factor them out, or you can divide both sides by the constant. So in other words, I'll have what a, or this is what I'm going to have. If I divide through by a ln 2, I'll have 1 over a ln 2, then d 2at is equal to 2at dt. So if you integrate both sides now, if you integrate both sides, you'll discover that this is actually our challenge. Now we want to integrate this particular side, so this is our challenge. So let's see what we're going to get when we integrate this particular left hand side. So if we integrate, remember the whole of 1 over a ln 2 is a constant, so you just bring it out. A ln 2 integral of d of 2at, is that okay, is equal to integral of 2 to the power of 8t dt. Now when you're integrating the something, whenever you integrate the something, this something can be anything in the world, so you're going to get that same thing. It's just like whenever you're integrating the x and you get x, is that okay? So whenever you integrate the something, you get that same thing. So the final answer to the integral of something like this is going to be 1 all over a ln 2, then integral of the something is going to be something, and the something in this case is 2at. Is that okay? And that is the integral of 2 raised to the power of 8t dt. So since we have established that this is the answer to this particular integral, okay, we are going to apply it here. So recall that the integral of 2 raised to the power of 8t dt is equal to what? Thank you very much. 1 all over a ln 2, then 2 raised to the power of what? 8t plus constant of integration. So that is what we are going to apply to this side, and this is what we are going to get by doing that. So p 2 to the power of minus t over 7 is equal to negative 20,000. Then when you integrate this particular one, you have 1 all over our a this time around is actually what is our a? Very good, it's negative 1 over 7. Is that okay? Then we have ln 2, then we have 2 raised to the power of negative t over 7, okay, plus c, like this. So I hope we understood why our a is minus 1 over 7 in this case, because 2 raised to the power of minus t over 7 is still the same thing as 2 raised to the power of minus 1 over 7 then t, like this. So this particular minus 1 over 7 is acting as a, so that's what we are going to do. So p that's 2 raised to the power of minus t over 7 is equal to minus 2 0 0 0 0, then resolving the brackets, 1 divided by minus 1 over 7 is actually minus 7. You have over ln 2. Then you now have 2 raised to the power of minus t over 7. We now have plus c. So if we open the brackets, or we are going to get p 2 to the power of minus t over 7 is equal to we have 140,000 over ln 2, then 2 raised to the power of minus t over 7, then plus c. If we multiply, or if we divide through by t, by this particular term over here, 2 raised to the power of minus t over 7, we'll have p is equal to 140,000 over ln 2. Okay, then 2 raised to the power of minus t over 7 cancels out. Then you now have c divided by 2 raised to the power of minus t over 7. So if you apply the law of indices, the law of indices is 1 all over 2 raised to the power of minus n is equivalent to 2 raised to the power of n. You get p is equal to 140,000 over ln 2, then plus 2 raised to the power of t over 7 c. Is that okay? So this is the general solution, okay, that models the amount of mosquitoes present in the system at any given instance of time. The general solution that models the amount of mosquitoes present at any given instant of time. So the only problem is that we need to find c, and c can still be found using integration. Our initial values, sorry about that. And initial values is that at the initial start of this particular system, the count of mosquitoes was 200,000. So p of 0 is equal to 200,000. It actually means that p is 200,000, and this is actually p naught when t is equal to 0. So anywhere you see p, you put 200,000, and anywhere you see t, you put 0. So we have 140,000 over ln 2, then plus 2 to the 0 over 7 c. So 2 to the 0 over 7 reduces to what? 1, because 0 over 7 is 0 and 2 raised to the power of 0 is 1. Then c times 1 is c, meaning that when we make c the subject of the formula, c will be 200,000 subtracted from 140,000 divided by ln 2. So I'm not going to evaluate this here. I'll leave this for you to explore what the value will be. So it now means that finally my p of t is actually 140,000 over ln 2 plus 2 raised to the power of what? T over 7 multiplied by c, and c is actually 200,000 minus 140,000 over ln 2. Is that okay? So you may be expecting that this particular system of equations, or this particular model that we use, will give us some kind of expected results, but don't be surprised. The kind of results that you're going to get, it may not look like what you want. And the reason why it may not look like what you want is because we have now taken care of the scenarios whereby other animals, other birds, they take away 20,000 mosquitoes per day. But the ideal scenario of this particular system tells us that after every 7 days, after every t equal to 14, or multiples of 7, 14, 21, 28, and so on and so forth, that the final p that we'll be getting will be 2 times the initial size. But because we have taken note of the fact that after every 1 day 20,000 mosquito goes away, then this may not give you the actual results that you will expect on a normal day. will not give you the actual results that you'll be expecting to get. So I want us to take note of that. So you can try plugging in different values of t, that's in terms of multiples of 7. So if you put 0, that is like the start value. If you put 7 is week 1, if you put 14 is week 2, if you put 21 is week 3, and so on and so forth. So if you put those values, see what you're going to get and try to compare it with what you may expect, then make the judgment by yourself. But this is just an example of application of differential equations. I still want to leave this particular problem to many critics and to many further analysis, but this is the way I think it should be solved. And if you have any questions, if you have further comments, please post it on the comment box. And if you feel there is still a better way of solving this problem, you can post it on the comment box. For now, thank you for watching. Thank you for going through the stress of watching this particular video. Of course, there are different ways of solving this particular problem and still arriving at the same answer. Remember, we made the transition from exponential negative ln 2/7t to correspond to 2 raised to the power of minus t/7. Now, someone wouldn't have done this particular transition. Someone would have still worked with this particular value. Okay, someone would have still worked with this particular value, and guess what he's going to get? In place of this particular guy, he's going to get exponential ln 2t/7. This is what he's going to get. So I want you to know that exponential ln 2/7 multiplied by t is still in every way equal to 2 raised to the power of t/7. It just depends on how good you are at playing around with your law of indices and law of logarithms. Okay, so someone would have solved with this particular way and arrive at this point, no problem, you're still on track. Okay, so this is just like a more sweeter way of leaving our answer. So I'll leave it to you here, and I'll hope to see you on the next video where we'll tackle another problem on application of differentiation. So till then, don't forget to please like, subscribe, please subscribe, share to your friends, please, and hit the notification bell to stay updated. So till then, take good care of yourself. Peace.